Welcome to Module 3, where we will explore the testing of DC machines, focusing on Swinburne's test and Hopkinson's test. Swinburne's test is an indirect method of testing DC machines, named after Sir James Swinburne. It is the simplest and most commonly used method for shunt and compound wound DC machines. This test helps determine the efficiency of the machine at any load by measuring no-load losses separately. Here is the circuit diagram for Swinburne's test. It shows the connections and components required to perform the test. This diagram illustrates the setup to determine the armature resistance, which is a crucial part of Swinburne's test. To perform Swinburne's test, adjust the machine speed to the rated speed using the shunt regulator. Record the readings of E as 0, if, and supply voltage V. Compute the armature resistance RA using the VI method. The no-load armature current, input power, and copper loss are calculated using these formulas. Constant loss is also determined to evaluate the machine's efficiency. Swinburne's test is convenient and economical as it requires minimal power from the supply. The efficiency can be predetermined at any load since constant losses are known. However, Swinburne's test has some disadvantages. It neglects iron loss changes, cannot ensure satisfactory commutation on load, and does not measure temperature rise. It is also not suitable for DC series motors. Hopkinson's test is another method for testing DC machine efficiency. It is a full load test requiring two identical machines coupled together. One operates as a generator and the other as a motor, making it also known as the back-to-back or regenerative test. This diagram shows the circuit setup for Hopkinson's test, detailing the connections between the motor and generator. If there are no losses in the machine, no external power supply is needed. However, due to voltage drops, an extra source is required. The external power compensates for internal losses, making Hopkinson's test also known as the regenerative test. In Hopkinson's test, two identical machines are coupled. The motor's shunt field resistance is adjusted for rated speed, and the generator voltage is regulated. The machines run at rated speed and desired load by varying field currents. The efficiency calculation for Hopkinson's test involves determining the motor input and generator output. Both machines operate at the same efficiency, denoted by eta. From the efficiency equations, we derive the input to the generator and output of the motor. Armature copper loss in the motor is also calculated. The armature resistance of both motor and generator is considered. The power drawn from the external supply is used to compute the stray losses, which are assumed equal for both machines. The total losses in the generator are calculated to determine its efficiency. The formula involves the output and input power along with the losses. Similarly, the total losses in the motor are calculated to determine its efficiency. The formula includes the motor input and the losses. Hopkinson's test is economical as it requires less power. It allows testing large machines at rated load with minimal power consumption. Temperature rise and commutation can be observed, and efficiency at different loads can be determined. However, Hopkinson's test has its challenges. Finding two identical machines is difficult, and they cannot always be loaded equally. Separate iron losses for the machines are hard to obtain, and operating at rated speed can be challenging due to varying field currents.